Okay. So let's officially start. Let me welcome everyone to this first talk of the YRTG series after our summer break. I'm happy to see that we have some people around, although it's still summer and it's still warm, and there's the beach and the lake and so on. It's good that it's nice to see that people still choose to have a nice physics talk rather than going for a swim. I wanted to say a couple of things first before we start the talk proper. Some introductory notes. So first of all, I just wanted to announce once more, although we already wrote this on the email, that we have good news regarding this YRTG project. We're going to have now a series of expert talks by people that are more established in the field, so not necessarily by our peers, by PhDs and postdocs, but rather by people that have generally more experience. And the expectation is that these talks will be pedagogical and will be introductory, and that they will be a good opportunity for the rest of us that are younger, so this in the context of this junior idea, to ask questions and get some contact with these more experienced people. We have a nice plan in principle, so let me show you what we have prepared really quick. Just a moment. So, and also an announcement. So if you go here to our upcoming events, you can see that we'll have our expert series. We start with string field theory by Ivo Sachs from Munich. Then we'll have a talk on group field theory by Daniele Oriti. Then a talk by Renata Lol on causal dynamical triangulations. And while we haven't put this on the website yet, I can also inform you that after Renata Lol, we'll have a talk by Carlo Rovelli on loop quantum gravity. And as I said, the idea is that this can be a good moment for everyone to learn about these different approaches to quantum gravity and also get some contact with these more expert researchers. So that's the first point. The second point has to do with the rules for the seminar. So let me just remind you regarding questions. We'll have a talk of more or less 45 minutes plus discussion in the end, which can last as long as we want. You can ask questions during the talk. You can also write those questions on the chat. You can either raise your hand to ask the question, or you can write the question in the chat. And in case you might want to ask a question in an anonymous manner, because you feel like that would be better for some reason, then you can also make use of a Google form that we're going to put on the Zoom chat that you can access so that you can ask that anonymous question. Right, and that's it. So without further ado, let me introduce Davide. Davide, I don't know if you want to start your screen share, please. Please go ahead.
Yeah. Let me try to do so. So I'll start, as I was saying before, right? This is the first time in my life I'm using Canva for a presentation to make it a bit more colorful and all of that. So I hope everything goes fine, right?
It's working well on this side. So yes, so Davide, he studied his master's degree in Munich at the LMU, and he's still in Munich at the Max Planck doing his PhD on the general topic of string theory and geometrical flow equations. He's also an avid science communicator. Indeed, he also has a YouTube channel more for our Italian friends. And again, for our Italian friends, I'm very sorry that I'm probably going to butcher this name. The channel is called Spazi Attorcigliati.
That's perfect. That's perfect.
Find the link to the YouTube channel also on the chat. It's probably also on the usual channels of social media, so you can also follow him there if you so wish. So let's welcome Davide on the topic of what string theory might tell us about quantum gravity. Please go ahead.
Thank you very much. I wasn't expecting you to mention my other life, like my second identity. I'm really bad with social media, so you'll find me, but it's do not expect much. So first of all, thank you very much for organizing not only this talk, but inviting me and all of that, but also the whole project of this young researchers in quantum gravity thing. I think it's truly important to try to build bridges and depolarize the subject. That's my strongest take. That's why I want to stress that do you see my pointer? Right? Okay. Yes. This might here is the most important word of the whole talk, right? Because quantum gravity is a very hard problem to tackle. We all know this. People have different intuitions, interests, right? So one might be more interested in getting I don't know, a general covariant diffeomorphism invariant quantization procedure, or to reproduce some kind of perturbative expansion with scattering amplitudes, with Curie UV divergences and all of that. But in the end, we really need to tackle a super hard problem, which is by no means done to be solved. So I'm really happy to try to discuss and share ideas. They might be bad ideas, but I'm happy to share them. So my personal research has to do with the Swampland Program, which is something that was born inside the string theory community, but somehow started working on its own. It's tied to the string theory community, but there are many ways of working in the field, and some of them are really kind of decoupled to the proper string theory, right? The whole construction with branes and strings and extra dimensions and all of that. So it tries to be a bit more broad. So that's why I entered it, right? It tends to be the most open one inside the community. So anyway, let me start with a brief outline of the structure of the talk. I hope everything once more goes fine with the presentation. I'll start by the standard textbook presentation of string theory. I'll keep it extremely soft with just a few equations, I have no idea how many of you have seen string theory. I do not assume anything, so some just basic knowledge of QFT plus GR, and I'll just try to outline the main features of the theory, right? Just for us all to know the graviton comes from in string theory. That's where I want to get, right? Which is the second point. Where is gravity? Why string theory became a tool for some people interested in the problem of quantum gravity. Where does the graviton come from? Where do Einstein field equations come from? Where do gravity sources come from in string theory? These are all questions I'll try to answer in the talk. And then I'll go to phenomenology. I'll try to argue why I think string theory phenomenology is not an oxymoron, and why I think there's something interesting to say, in particular concerning the Swampland program. Please, as we said before, feel free to ask questions whenever you want. I'm not sure I'll be able to answer. I'm just a PhD student, right? I'm far enough from my string theory courses to have forgotten the right answers, and far enough from being an actual expert for not knowing them enough. So sometimes the unanswered questions will be on me and not on the string theory community. I take full responsibility of that. So let's start from this big question, like, what is string theory? I've stolen this nice picture from the internet, and I'll give you as I said, the textbook answer. It is the quantized supersymmetric Wordsheet theory for a one-dimensional string propagating in these space-time dimensions. This is extremely convoluted. I gave you the definition because there's a lot of interesting buzzwords here, right? We have a one-dimensional string. We have D space-time dimensions. We'll talk about this D. Where does this D come from and how it gets fixed in string theory? We have this damned word, supersymmetry, and I'll address how supersymmetry comes into play in string theory. This is an important thing to stress, right? And it's clearly a quantum theory, okay? So what are the main features of string theory? I'll get to the equations on the bottom of the page afterwards. So let me start by making it clear. We are discussing perturbative string theory. Perturbative string theory is not the full theory. We do not have control. I'll get to what it precisely means afterwards, but we have no full control on the actual string theory, right? There are a few ways to try to understand the problem, like the full non-perturbative formulation of the theory. One of the most promising ones, by being extremely hard on the mathematical side, so there's not many people working on that, is string field theory, which is something Professor Sachs will discuss in a few weeks. So you can ask him all the interesting questions about the full non-perturbative formulation of string theory. I'm pushing the hot potato to him because I guess that in perturbative string theory is not really nor possible nor appropriate to fully address questions like background independence, diffeomorphism invariance. I guess it's somewhere in between a full satisfactory diffeomorphism invariant theory or background independent theory and a non-background. There are some pros, some cons. I'm not fully satisfied with the perturbative theory personally, okay? Because I'm kind of strict with these kind of definitions. So for such questions, you'd better refer to string field theory. Here we're discussing perturbative string theory. How do we do so? We try to develop, I'll skip the motivation, something which is a two-dimensional extension of the so-called word-line quantization for particles. You all know that in quantum field theory, you can create and destroy particles, right? With your creation annihilation operators for your fields, right? There must be something similar for strings, but if you cannot write your full quantum field theory, you can still take a particle, assume your particle number is fixed, write down its word line action, right? Which is nothing more than the Lorentz invariant length of its word line, and couple such a particle to background fields. This is something people do in quantum field theory and recover no results, okay? So you write the action on the word line and you embed such a word line in a space-time manifold. This is similar to what we do in string theory, okay? So we take a one-dimensional object, we call it a string, a relativistic string with a Lorentz invariant action. It can be either open or closed. It doesn't matter really right now. I mean, closed strings are more interesting on the gravity side, while open ones are more interesting in trying to reconstruct gauge theories with free gauge groups and all of that. So I'll mostly focus on closed string. You let such a relativistic string propagate into spacetime, spanning some kind of two-dimensional surface. We call it a word sheet, fully analogous to the word line. Such a surface is typically parameterized by two parameters. We call them tau and sigma. Tau is some kind of time direction. Sigma is nothing more than a parameter along the string. This is the newly introduced parameters when going from the particle to the string, clearly. Your theory must be invariant under reparameterization of tau and sigma, which has nothing more than parameters on your 2D analog of a word line. So you have to take care of that. And we write down the word sheet action for the string. Here you have the word sheet action for a string for a bosonic string. I'll get to that later. We'll tackle supersymmetry later, which is what brings us from bosonic string to superstring. But all I have to say concerns the bosonic part of the theory, so we'll stick to that. Here you see the action after it has been massaged a bit, right? You start from your action for the word sheet, which is nothing more than the area of the word sheet, the Lorentz invariant area. You introduce some new degrees of freedom to make it more treatable. This metric on the word sheet, A and B parameterize tau and sigma, while mu and u are space-time coordinates, space-time Lorentz indices, right? So what you do is you write down an action for the string defined on the word sheet. Here you have a two-dimensional integral because you're integrating over the word sheet for the string's coordinates, right? From a space-time perspective, and this is fully analogous to a word-line quantization for a particle, I want to stress that. From a space-time coordinates, these x mu are just components of a vector parameterizing the string, like telling you where the string is in space-time. From the word sheet perspective, these are nothing more than D bosons, right? D bosons, D scalars, right? Nothing more than that. And you can either look at them from the perspective of your word sheet or of space-time, right? So you do what you would usually do. You write down your equations of motion, you solve them, you quantize your theory, and do all that. So what you see here on the right is the expansion for left and right modes for a closed string, right? It's simple solution to the equations of motion. You have some offset, we call it x mu, some alpha prime, p mu, sigma minus, sigma plus and sigma minus are just light cone coordinates on the word sheet, tau plus sigma and tau minus sigma, nothing special, right? And here you have your modes. Alpha prime is the typical parameter of the theory. It is related to this T, which is the string tension, and it tells you the length of the string. As far as we are concerned right now, alpha prime is the only free parameter of the theory. Alpha prime sets the length of the string, and that's it, at least in the space-time dimensions, but we'll get there. So this alpha mu n and this alpha tilde mu n you see here are the coefficients of your expansion in Fourier modes for the string modes, right? And when you quantize the theory, they clearly become your creation and annihilation operators for string excitations. So in this kind of quantization, you have a fixed number of strings. If you want to create or destroy strings, you must go to string field theory, but at least of word sheets, strings can branch and rejoin, but you cannot have multiple create and destroy word sheets. But you can create and destroy string excitations. So with your creation and annihilation operators, you can put energy in a string or remove energy from a string. Okay, so you quantize your theory. You can do it in 3 different ways. since we have introduced some extra redundant degrees of freedom on the worldsheet, we must fix them and they become constraint equations. So we can either fix them before quantizing, fix them after quantizing, or go to a full different path integral quantization of the theory, okay? But we'll discuss the three different things afterwards when we're discussing the number of space-time dimensions. The point is that at this stage, you get your vacuum. You get a vacuum state for your string on the worldsheet, and you can act with creation operators in order to put energy in that vacuum. By doing so, you notice that your creation and annihilation operators have a space-time index, a Lorentz index, which comes straight from the fact that you are decomposing as scalar bosons the components of a space-time vector, right? A space-time position, not even a vector. So by doing so, you add Lorentz indices to your vacuum, and you create space-time fields. That's what, in popular science, people in outreach, people tend to say that fields come from different vibrations of strings in string theory or whatever. This is really what they mean. You have a vacuum, you act with creation operators that carry a space-time Lorentz index, and by doing so, you create space-time fields. Then you clearly have to decompose them into irreducible representations of the Poincare group. Everything is done at this stage, everything is extremely formal, because we're working with a 2D conformal field theory. You have conformal symmetry on the worldsheet, and this allows you to really constrain your theory and treat everything extremely in a perfect, super nice and way. People, mathematicians tend to like it a lot, right? 2D CFT is so constrained that you really fix all your amplitudes, everything is super nice, super fine. Sadly, our world is not a 2D CFT. So let me stress three specific aspects of string theory. Like this.
Sorry, Davide, can I interrupt you a moment there, because we got a question on our form already.
Sure.
So the question says, your textbook definition seems to privilege a supersymmetric theory, but I heard that there are actually many string theories. Which criteria did you use to choose the definition?
No, this is one of, thank you very much for the question. First of all, I think there's a lot of misconceptions going around on, I tend to be strict when I say things, right? And I tend to, there's a lot of misconception around the supersymmetry in string theory for two main reasons. The first one is that we have this difference between the worldsheet theory that gets embedded into spacetime. So you really have your worldsheet theory from which a spacetime theory comes. And this comes from the fact that we're doing a purely worldsheet quantization perturbative. I mean, the full non-perturbative theory must be a single one with spacetime emerging and all of that. But at this stage, we have a worldsheet theory, which works as a nonlinear sigma model from which we get a spacetime theory. So supersymmetry on the worldsheet theory is different from supersymmetry in spacetime. Supersymmetry on the worldsheet, and I'll get there now, is required for consistency. And I'll explain you why. But this has nothing to do with supersymmetry in spacetime. I personally do not like supersymmetry in spacetime, so I do not privilege it. I think it should be broken at very high energies or in 10D or even not be there in spacetime. So supersymmetry on the worldsheet is really a formal trick. I'll get there now, okay? Because here, this action is not supersymmetric. You only have bosonic fields. You have D, but D is the number of spacetime dimensions, bosonic fields in 2D, right? Then you have your spacetime theory coming from this, but let's stick to the 2D theory. Let me start from D, the number of spacetime dimensions. Then I'll move to supersymmetry and answer the question, if I may. Is it possible? Okay, so string theory has this weird feature in which the number of spacetime dimensions is fixed by internal consistency. It's not a number you can tune from outside. Sadly, it's not 4, otherwise everything would be super easy, and that would work for our priors in a Bayesian sense. But when you quantize your conformal theory, you must require it not being anomalous. I told you, your 2D theory is conformal, and you have your space-time fields coming from worldsheet states, right? So what you do in order to ensure your quantum theory doesn't break your conformal symmetry is compute scattering amplitudes on the worldsheet, right? You take your states, you scatter them, and you compute beta functions which involve your space-time fields, which come from the states, right? In order for conformal symmetry not to be anomalous, you impose all such beta functions to be 0. You know if some beta functions are not 0, you clearly get some trivial behavior with a scale and whatever, running coupling on, and all of that. So you must have all beta functions being 0 for your theory to be conformal at a quantum level. So that's what you do. And by doing so, you not only derive the equations of motion for your space-time fields, but you also derive in the path integral formalism, imposing it not to be anomalous. You derive the number of space-time dimension, and you fix that to 26 in the old bosonic string theory, which is the one which is non-supersymmetric on the worksheet, which is problematic, and I'll get now to why, and 10 in superstring. So we'll keep 10, okay, which is what everyone agrees today on. So you get D equals 10, which is weird. If you want to quantize your theory with standard canonical quantization, either imposing your constraints before or after quantizing, you need D equals 10 either to have Lorentz symmetry in your quantum theory or unitarity. Typically, if you impose constraints either before or after, you get one for free, and you have to get the other by imposing D equals 10. Okay, so that's how it goes. Supersymmetry on the worksheet. Then we'll get to, this is consistent with having a low energy theory in 4 dimensions. We'll get there. There are experimental bounds, but we'll get there. Supersymmetry on the worksheet in order to address the anonymous question I received. If you keep the action I showed you before for the worksheet theory, you have a few problems. The main one is that you have tachyons in space-time. Your theory is unstable. It simply doesn't work. You all know that tachyons are really bad for your theory. The way to cure tachyons is to introduce some fermionic degrees of freedom on the worksheet, meaning that your string can get fermionic excitations, which are not precisely clear from a classical point of view, but they are something that we need for a quantum theory to be consistent. So you get, I mean, the classical intuition of a string moving in spacetime gets a bit less clear when you introduce fermionic degrees of freedom, but that's what you do, right? You add a new piece to this action on the worksheet with fermionic fields, and everything goes fine. You remove tachyons, the number of spacetime dimensions goes from 26 to 10, which is the number I mentioned before, and you do not really need to have supersymmetry in spacetime. That's the answer to your question. So you have supersymmetry on the worksheet. From that, you derive your spacetime low energy theory, right? And in 10 dimensions, you typically have supersymmetry. You typically have it. You can have breaking. You can do it without, like you can do some versions of the spacetime theory in 10 dimensions without supersymmetry. You can still do that. But even if you have supersymmetry in 10 dimensions, right, it can either be broken at super high energies, right? Super high energies. There's a good friend of mine who's studying, like Ivano Basile. I will mention one of his papers, but on a different topic. He studied this supersymmetry breaking in the very high energy regime. Is something people are working on. So I strongly encourage you to look at his PhD thesis on the topic. It's extremely interesting. But if you do not break your supersymmetry in 10 dimensions, you have it. When you move to 4 dimensions, there are so many ways in which you can destroy supersymmetry before getting to 4 dimensions. In particular, we'll get to compactification. Compactification is the idea that, okay, the theory tells us spacetime has 10 dimensions. We see 4. We either throw the theory away, or we find a way to construct a 4D phenomenology. The choice is up to you. I stick to the second, but it's totally reasonable to stick to the first one. Typically, this kind of choice has to do with your idea of how heavy an ontology is if you have stuff and structure on spacetime. I mean, that's a full different subject. But what you typically do is, instead of considering the full 10D spacetime, you consider a Cartesian product, or even a non-trivially fibered one, but a Cartesian product, let's keep it simple, between a 4-dimensional spacetime, which is the one in which we live in, and 6 compact dimensions, right? So, and a 6-dimensional manifold. Geometrical properties of such a manifold define your phenomenology in 4D. And this is where the great number of choices you can make in string theory comes into play, but we'll get to that in the last section of the talk. So if you want to do 4D phenomenology, you have to remove 6 dimensions by making them, there are many different ways, but the most common one is to make them really small, right? In a compact manifold. If you precisely choose such a manifold so that this happens, you can still keep supersymmetry in 4D, but this is by no means necessary, right? By no means. So it's perfectly reasonable not to have supersymmetry in 4D. I mean, you really have to tune your 6D manifold to have supersymmetry. People did that because there was some kind of merging between the supersymmetry community or a portion of the supersymmetry community and the strings community, and people tended to prefer supersymmetric theories in 4D because they could deal with them more and all of that. But typically, there's a lot of work in non-supersymmetric string. There's been a lot of work in the last 30 years. And in general, you do not need that. These Calabi-Yau manifolds people mention a lot are the ones that typically allow you to preserve a part of your supersymmetry in 4D, but this is not needed in a sense. So you can totally work with non-supersymmetric theories. So as I said before, perturbative string theory has some issues with making it clear your theory's background independence. Indeed, when you quantize a perturbative theory, you need to fix a background. You can look at that as a kind of gauge fixing of your diffeomorphism invariant. I mean, depending on your rigor, you can consider it as you like. But I would say that I'm not satisfied in the way it emerges from perturbative string. There's no consensus on the topic in the community. But on the other side, if the non-perturbative regime is fully out of control, we'll get to some non-perturbative effects. I'm being a bit drastic here. The perturbative one is well behaved. You have amplitudes, you can scatter your fields, you have no UV divergences because you have introduced some kind of length, minimal length given by the string. So these warships have no point-like interactions because they are extended objects. So you remove UV divergences coming from fields not being well-defined as point-like objects, you know, all those things about quantum fields. So in a sense, if you like to compute perturbations and scattered amplitudes, I know people are not satisfied with this, but the theory works fine there. You can scatter stuff and compare that with your quantum field theory predictions after having done all these steps. 4D phenomenology, I'm getting there. As I said, the requirement of worldsheet conformal symmetry not to be anomalous in your quantum theory fixes the equations of motion for spacetime fields in 10 dimensions, right? Then, and at this point, the only external parameter is the string length, the only one. You can make different choices when writing down your 10D theory, but it came out that all such choices are dual to each other, fortunately. So there's no a difference between the various 10D theories. But you have to go down to 4. You have to go down to 4, and by going down to 4, you have to choose the shape of the internal dimensions, and by doing so, you fix the 4D phenomenology, but you have a huge room for wiggles in the 6 dimensions. So you can make many different 4D phenomenologies by choosing different shapes of the 6 dimensions. And this is a critical issue. It is an issue. So this is what we try to address in the so-called Swampland program. We have a hope that this can be solved, and I'll explain you how after having introduced our old good friend, the graviton. Also, this picture is stolen, and it's just, you know, it's just nice. The reason for which people got interested in string theory as a way to try to tackle from a weird perspective the problem of quantum gravity is that when you derive your string states, right, you write them down, you take your vacuum, act with creation and annihilation operators, decompose them into irreducible representations of the Poincare group, you get a spin-2 massless field, right? You need that. Actually, it's really hard. You cannot think of string theory without having a graviton. Indeed, you call this a graviton not only, you all know those arguments by Weinberg and others on how spin-2 massless fields really have not much room for different actions, but here you get Einstein equations explicitly, right? When you compute the equations of motion by making 2 gravitons scatter on the worldsheet and imposing their beta function to be 0. By doing that, you get Einstein field equations plus further corrections, plus high order corrections, right? In terms, you have this kind of expansion in terms of the string length, in terms of alpha prime. So you have Einstein equations plus some corrections. So this is why I tell that in the perturbative regime, things are going fine. It's a bit harder to construct the full non-perturbative theory. I mean, there's a lot of open issues here, right? This is a work in progress. So how to go further? Quantizing perturbative strings requires a background, as I said, which accounts for some kind of gauge fixing of diffeomorphism invariance. It might be wishful thinking just to consider it, might be much deeper. I try to keep it compact. So you should really refer to more advanced techniques to tackle this problem. I stress it once more. String field theory, I think that the whole discussion around cobordism in string theory can give you a backdoor to settle the thing, but we'll get there later. Fortunately, when you compute your equations of motion, you get the full Einstein's equations, not just the linearized ones, and you can solve them and see that your theory has a lot of interesting non-perturbative objects when you solve the equations of motion for your fields, even in the 10D theory. You have D-branes. D-branes are objects which are of various dimensions, right? You have 0 branes, which are points, 1 branes, which are strings, 2 branes, which are 2-dimensional objects, and so on and so forth and so forth and so forth. All these objects source gravity. They source gravitons, they bend space-time, and you can use them in many, many, many different ways. The cool thing about branes is that they come out in 2 ways in the theory, which were a priori completely different. Polchinski proved they are the same exact non-perturbative object. In one way, they come here as gravity, extended gravity, so non-perturbative gravity sources. And in the other sense, they come out when you consider open strings, and which are really open strings, nothing more than that, end on some non-perturbative objects, and you find that open strings really end on D-branes. So they are not only gravity sources, but they are where open strings get attached to, in some weird way, similar to what we have seen for the graviton, sourcing gauge fields. So that's why people got really interested in D-branes. You have these objects, they source gravity, and they have gauge fields living on them. You can, with all these ingredients, you can really construct a lot of stuff. You can take stack of branes, bend them, you can make them intersect, and by doing so, you can really construct gauge theories localized on the branes, which with more or less whatever gauge group you like. You can have Yukawa couplings, you can have some kind of Higgs mechanism on the brane, you can have a lot of stuff. There's some problem. There's a nice chapter. I suggest you, if you're interested, I suggest you to take a look at it. On Barton Zuibach's book on recovering the standard model from string theory, there's some problems with electroweak symmetry breaking, with achieving some kind of supersymmetry breaking when going to low energy. But for what concerns finding an analogous to the Higgs mechanism and finding the correct gauge group and the matter content, this is not so problematic with stacks of branes. So from a gravity perspective, which is a bit more interesting for us, D-branes have been used for 2 main things. The first one is the old Strominger and Waffa computation of the number of black hole microstates in string theory. What they did was taking a lot of branes, wrapping them, constructing a black hole, right, by wrapping a lot of stuff with a lot of gravity being sourced, and computing the number of quantum states of the theory, and they precisely got the area law for the entropy, which is good. I know this is one of the tests you like to achieve. I know there are other alternative computations, and they're super interesting. I guess this is something quantum gravity theories have to go through, in a sense, computing area law, and by no means string theory is the only one in which this result is achieved at this point. So yeah.
Yeah, thanks. Maybe just to ask, do you know if the factors also gotten correct in these computations, the factor of 1/4 in the entropy calculations?
Yes. They got it correct for supersymmetric black holes at the time. It was the 9th. Now people have pushed it forward. Like, the cool thing was getting the 1/4 correct, right? Because area law tends to be a bit more general, right? And all of that. So they got it correct, and people got extremely excited about it, extremely excited. But they had supersymmetry at the time. Now people have pushed the boundaries of the result, even to more realistic black holes, I guess. But I'm personally not an expert on the subject. So if you want to look at some literature, I suggest to take a look at the work by Alessandra Gnecchi. She's a colleague, and she's been working for all her life on black holes, and she's really an expert on black hole microstate counting. So you'll probably find a lot of results there. But there's a lot of reviews on the subject. If you look for microstate counting in string theory, you get a lot of stuff, and you can see where people got. Okay, I'm not an expert, so I don't want to. You know that usually in scientific debate, there's a lot of there's a consensus to form on where we actually are, right? So there's optimistic people pushing it a bit further, pessimistic people holding it a bit behind. So I never know where to put the bar. So we surely got beyond what Strominger and Waffa did, but I'm not precisely sure where we got. Okay?
Okay, yeah, thank you.
Oh, you're welcome. Thank you for the nice question. So the other super interesting result, we are still in the 90s. The 90s have been a great time for string theory, is realizing via D-branes an explicit example of holographic correspondence between a gravity theory, namely anti-de Sitter in type 2b, which is just some technical thing, string theory in 5-dimensional anti-de Sitter spacetime, and n equals 2 super Young-Mills quantum field theory on the 4-dimensional boundary. Clearly, none of this is meant to describe a universe, but you actually, via D-branes, you actually have an explicit construction of a holographic correspondence between a gravity theory and a quantum field theory, a supersymmetric, in this case, quantum field theory with no gravity. So this was super interesting, and there's a lot of work going on. I mean, ADS-CFT, I guess, has become some kind of independent field, which got slowly decoupled from string theory. So there's a lot of work in ADS, which is more or less string independent, and some other work in ADS-CFT, which is string reliant, I guess. And this kind of discourse will become relevant also in the context of string theory phenomenology, where I'm getting now. So people got worried. People got extremely worried, and this is true, when they realized that by choosing the shape of your 6 internal dimensions, first of all, you had to do this thing, right? You do not get D equals 4 straight from the theorem. You have to do something like this. And you have a lot of freedom in doing that. Plus, you have some non-perturbative effects to consider. Some moduli, some fluxes. Moduli have to be stabilized. They should not just decay and all of that when you construct your 4D theory. There's a lot of stuff you have to do. So there's a lot of choices you have to make, even if at the beginning you already have had the string length. And by doing so, you can construct many, many, many different superstring effective theories in 4 dimensions, which is a problem, right? So the number is huge. People expect it to be finite, which would be great, but it's huge. It's like 10 to the whatever, 200,000, some huge number just for F-theory vacua, which are a specific subset of such 4D phenomenology. So there's, I mean, there's as many vacua as the number of manifolds you can choose for your internal dimensions, plus all the freedom you have in choosing how to stabilize your moduli and all of that. So there's a lot of freedom. And people got worried because one question straight comes into your mind, pops into your mind. So you define the swampland, the landscape, pardon, as the set of 4D low energy quantum field theories coupled to gravity that can be constructed as low energy limits of string theory. Okay, all those vacua we were discussing before. And if any consistent QFT, like whatever consistent, where for consistent I mean just not clearly and explicitly inconsistent, like you want Lorentz invariance, locality, and all those things. But if any consistent QFT belongs to the string theory landscape, namely if any consistent QFT can be constructed as some kind of low energy limit of string theory, you would have no 4D predictive power, right? This is an issue. This was an extremely important issue, right? I mean, no one cares about 10D super high energy predictive power if you cannot make predictions about 4D world and low energies and whatever. I mean, yeah, sure, we can postpone the studies on your research line until we get to super huge accelerators big as Jupiter and whatever, but you really want 4D predictive power in 2022. So this was a problem. And people tried to address this issue, and fortunately realized with different levels of rigor. We'll get there later. I mean, I'll mention how rigorous this all is afterwards. Starting from, I mean, it started in 2005, 2006, but actually it kicked off around 2015. It became one of the main things in the string theory community, surely in the string theory phenomenology community. People realized there are constraints on the kind of theories you can achieve from string theory, namely features they have and share, and you cannot avoid having. And such constraints seem to be strong. Now, here I included a picture people in the string theory community see at every single talk on the Swampland program So I tried to find some alternative version of the picture on the web. So I stole this, right? It's stolen. Here you start from string theory. Here, string theory is put into brackets. Here on the vertical axis, you have the energy at which you probe your theory, right? Because there's people trying to do this in a way which is decoupled from string theory, just using general quantum gravity arguments, right? But I'll get there. Like the reason for which I wanted to discuss the Swampland and the reason for which I like the Swampland a lot is that there's a part of the line of research which uses maybe string theory as an example, but really wants to derive some general statements. So try to derive general statements from semi-classical considerations and all of that. But anyway, here you have whatever theory you like, let's say string theory for today, and you take it to be extremely constrained. You are in the extremely high energy, so you have the one full theory that describes a universe, right? As you move towards lower energies, the kind of 4D phenomenologies and low energy phenomenologies you can construct increases, in the sense that your constraints, which become evident in the UV, loosen up, right? They loosen up. So you get a huge number of living here in the landscape, which is this nice place, a huge number of theories you can derive at low energies from the unique UV theory you have in the UV. Fortunately, people discovered that there's a lot of consistent QFTs, like consistent in the sense that if you look at them, they could be perfectly reasonable models of a universe, which are not explicitly Lorentz inconsistent from a Lorentz invariance perspective or no unitary or whatever. You have consistent QFTs that cannot emerge from string theory. Here, once more, is said quantum gravity because people try to generalize this and get a bit decoupled, but and a bit more safe with their claims. But in general, people try to people found that there's a lot of sticking to string theory QFTs in the low energy regime that cannot come from string theory. Okay, and this is cool because you have some way of distinguish between at least predictions and stuff which cannot be predicted from the theory. I mean, if you found a universe to belong to the Swampland, to the string theory Swampland, the theory would be fully falsified. Okay, so this is the cool thing in the sense, I mean, it's a research line, a new research line. There's a lot of work to be done. Some things are more rigorous, some others are a bit more sloppy and still need time to get developed. But at least it gives you a way to try to probe your properties, the properties of your theory in the low energy 4D regime, which is cool. So the aim of the whole Swampland program is to chart the space of 4D consistent theories, QFTs coupled to gravity, precisely, namely to derive the shape of the boundaries between the landscape and the Swampland. I mean, holy grail would be something like, okay, you give me a theory, a consistent low energy 4D quantum field theory coupled to gravity, and I can tell you whether it belongs to the Swampland and to the landscape, only referring to the properties of your 4D low energy theory. So this is what people want to achieve. Okay, how this is done, how to conjecture a Swampland conjecture. Typically now we are kind of sure about some features theories in the Swampland must have, or theories in the landscape. I mean, they're the complementary of each other, so it's equivalent. But many of such statements are in the form of the so-called Swampland conjectures, in the sense that you conjecture them and you try to collect evidence from them. So this is usually done in three ways. First of all, your Swampland conjectures should be consistent. I mean, this has to be taken with a grain of salt. We all know that we still don't know how really quantum gravity behaves, but at least you have some naive expectations on how quantum gravity should behave. For example, breaking of global symmetries. This is something people expect in general, like global symmetries not to be allowed or stuff like that. So you would like your Swampland conjectures to be consistent with your general naive expectations on how quantum gravity should behave, keeping that, taking that with a grain of salt. Then you have semi-classical considerations, typically coming from black hole physics. I mean, you have the information problem and all that stuff, and merging black holes and entropy bounds and all of that. Clearly, your Swampland conjectures must be consistent with resolving, in a sense, semi-classical problems of QFT plus gravity. And then you have known, oh yeah, sure, please.
Yeah, I would like to ask, what string theorists think about what conjecture might be more relaxable than others. For example, there's research done on asymptotic safety. You might know also Ivano's papers. So if it turns out that, say, asymptotic safety is not somehow compatible with the Swampland conjectures or other theories, then what would string theorists say they might be, or what would they agree on to relax from all of these conjectures?
So, as I was saying, I understand. Thank you for the question. It's super interesting, and this is a topic of debate, right? Clearly, what would the best thing be? Like, you have some scenarios, right? You take string theory, you take asymptotic safety, you take whatever quantum gravity theory you have, and you use them to separately constrain your 4D theories, right? How your 4D theories behave in this philosophy of the swampland, like following what Ivano and Alessia have done in their paper. So you can have two scenarios. Their landscapes intersect, right? So you have some common shared region in which QFTs are consistent with either string theory and asymptotic safety, or asymptotic safety and group field theories, or whatever you like, or they can be mutually exclusive. And at that point, you should really discuss them separately, and that would be a nice test, right? I personally think if you find separate regions of the low energy, I expect it not to be so, but if you find separate regimes of the 4D low energy theories, right? Finding evidence that a universe belongs to one or the other or none can update my priors on what theories are most promising or not. So that's, I guess, the most general. I mean, no one. So as I was saying, this first point is the critical one concerning your question, like how reliant the Swampland program should be on string theory, right? So string theory can be taken in two ways. You can say, okay, you have the graviton, you have a quantum theory, you have no control on the perturbative theory, but at least in the low energy, you expect it to at least achieve some of the features quantum gravity should have, might not be realized. So you take it as a kind of example and toy model of gravity, you don't believe it. Or you really take it as, okay, let's see if string theory, if our universe belongs to the set of theories that can come from string theory. This is far to be tackled, but I think that the right answer to your question depends on how reliant you want to be on string theory. People now tend to be a bit more reliant on semi-classical considerations when formulating Swampland conjectures. I think Ivano's is going in this direction, and known string theory vacua are some kind of test ground. You see whether they are consistent or not with your expectations, but there's a lot of room for wiggle. There's a lot of room for wiggle. That's what I would say. People in the Swampland community on this, it depends. Clearly, it's a new field. People strongly disagree with each other. So there's no common understanding of the subject, but there's some consensus of a few conjectures that are expected to hold true even outside of string theory, and some others that are really string reliant. Okay, so this really, I mean, the tensionless string conjecture, which mentions strings appearing as non-perturbative, that clearly has to do with string theory. People saying that gravity should break all global symmetries or gauge them or whatever, I think is not that reliant on string theory. And it really relies on some kind of general holographic arguments and some black hole naive arguments that do not really rely on string theory. I mean, we expect string theory to satisfy that. We would be surprised if it was not so, but really people tend to believe or have trust in the or expect the no global symmetries conjecture to be true even outside, either regardless of string theory, for example. Okay, so I think it would be a difference if asymptotic safety clashed with the idea that global symmetries should be absent, or with the tensionless string limit, or some kind of distance conjecture, which is really reliant on the idea that you have extra dimensions and all of that. So I guess this is the case. This is the kind of thing I would answer. It really depends. I made it long, but It really
No,
depends.
no worries. Maybe we can follow up later. Thank you.
Yeah, thank you. I hope you're at least slightly satisfied with the answer. I mean, it's hard. It's something I'm actually interested in. I mean, in my ideal world, you get a lot of landscapes from different quantum gravity. Well, they all intersect in a small point where you have a universe and all of that, and everyone is happy and friend. And this is a bit of wishful thinking. So general, as I was saying, nowadays it is common to back Swampland conjectures up with string-independent arguments, and that's why I'm arguing. I just want to argue that this whole Swampland idea might be interesting even outside of the string theory community, and that's why I'm extremely interested in that, and I try to push it or at least share it. And non-stringed aqua are really just some kind of test ground, right? Okay, they all share no global symmetries. Okay, whatever, they are consistent with the conjecture, they back it up, but they're not as much as an evidence as they were. But this really depends on who you are, right? The community is broad, the community is vast, and all of that. This perspective lies on the fact that quantum gravity in the extreme UV appears to be extremely constrained. And this is just a fancy, as you all know, a fancy way to say that it is hard to write down a quantum gravity theory. We're not in a setting in which we have a plethora of consistent, full non-perturbative quantum gravity theories that also admit a nice classical limit with all the mathematical caveats, but quantum gravity is hard, which is translated into it being extremely constrained. Hence, consistent quantum gravity theories are expected to share at least some common features, right? With different degrees of confidence. And Ivanov's work really tries to compare asymptotic safety with the Swampland, right? So here's a few examples. This is a nice map because the idea of the Swampland program is just to chart, right, the landscape and the Swampland. People started listing and formulating many conjectures. I've seen a nice plot that is going around the Swampland community. On the x-axis, you have the usefulness of a conjecture, and on the y-axis, you have the rigor of a conjecture. And clearly, you have a line going down. I mean, the most useless and broad conjectures are the one we trust more, and the most useful and constraining ones are clearly the ones we have less evidence for. So this is how it goes, sadly, in the world. But many of them are stated quite clearly. The ones which, at least in the context of string theory, is expected to hold true is the distance conjecture. There's a lot of evidence for the distance conjecture in string compactification. The idea of the distance conjecture is the following. Take your 4D theory. You have some fields. Such fields have some vacuum expectation values, right? So you can somehow look at the theory from the perspective of some kind of moduli space, which is charted by the vacuum expectation values of your fields. You would usually be able to displace them a lot, right? The distance conjecture claims that you should really not be able to arbitrarily displace your vacuum expectation values. Indeed, you should expect, starting from a consistent theory, you should expect, by displacing your moduli, your vacuum expectation values of your fields, you should expect something bad to happen. You should expect either to restore a global symmetry in the infinite limit, or you should expect an infinite tower of light states to become massless and enter your spectrum, other fields, right? To enter your spectrum and make the theory inconsistent. So the whole, I would say that the philosophy behind and the whole message of distance conjecture is, at least in the context of string theory, you should not expect field displacement to be arbitrarily big. This has to do partially with the idea that you should avoid the trans-Planckian fluctuations of your fields. So your theory should really account for such displacements. Then there's no global symmetries conjecture. You all know it, and I mean, I mentioned it a few times. Then there's this cobordism conjecture, which is pretty interesting in a sense. Is a way to try to generalize the no global symmetries conjecture. People, we can get there afterwards if you like. And the cool thing is that people have shown that many of these, there's a huge web of conjectures, the weak gravity conjecture and many others, the sitter conjecture and all of that. I mean, the problem of the sitter in string theory is something we can discuss afterwards if you want, but I'm not an expert, but I've been discussing it a lot. So I saw more or less how the consensus is now, but there's something going on for the sitter in the swampland, and people have shown them to be kinda related to each other. So this is cool. Like there's a web of connections among different swampland conjectures that make them a bit more solid. For example, when you connect one for which you have a lot of evidence to another one for which you have less evidence, or in which evidence is a bit less clear. One last remark concerning phenomenology, which I forgot to mention before. As I said, there are, going back to the idea of compactification, there are experimental bounds on the size of the 6 dimensions, right? Which is something like not so low, actually. People, how do you do that? Gravity leaks in every dimension you have. When you have extra dimensional models with extra dimensions, gravity becomes weaker, and you have deviations from Newton potential in the high energy regime. This is something you see in all extra dimensions model.
Davide, let me just interrupt you to tell you that we've passed now the 5-hour mark, the 17-hour mark. Okay, perfect.
Perfect. No, I wanted to say that the bound on this extra dimensions is set to something like a micron at the moment, which is huge. I was expecting it to be much smaller when I encountered this. And I suggest to take a look. There's a lot of literature going on viable phenomenologies, which should be tested with LISA, with the interferometers. People are really enthusiastic about interferometers in testing extra dimensional model and all of that. I mean, thank you very much for your time and help. I hope at least, I guess 7-8% of my talk was conveying information. And if you have any question, please feel free to ask. Once more, I don't know if I'll be able to answer, but I'm here. So you can also discuss. I mean, if you want to write me an email or send me a question or whatever, we can try to sort things out together.
Thank you very much, Davide, for the talk. Let me activate here the clapping emoji thing. There we go.
There's
I open now the discussion session. So let me ask, does anyone want to ask something to Davide?